Here we will see about the top program module capability and introduction. That's the one used to generate the inertia forces when we are doing the transportation analysis of any cargo. The top program module is used to generate forces typically encountered during the barge transportation of structures. When we are transporting the structures using the barge transportation, there would be inertia forces the structure would be encountered. Those forces will be generated using this top program module. The program generates inertia forces due to acceleration of the structure in the form of joint concentrated and member distributed loads. So it's clear this program it calculates all those inertia forces from the acceleration of the structure. We can get the inertia forces by multiplying the acceleration of the structure with the mass of the structure in the form of joint concentrated joint concentrated member distributed load. Suppose if you have the structure like this, and it will create the inertia forces, and it will apply at the joints, and then it would distribute the member load also. This is how it calculating the inertia forces. Program features, if you see, the tau requires a SACS input model file. So we need to have the input model file. From the model file it will calculate the member segments and member properties, and tau input file for the execution. So the program, so there are two inputs, model file and tau input file. The program creates an output structural data file containing the model load cases consisting of inertia loads generated by the program. Some of the main features and capabilities of tau program, if you see, it creates load case for x, y, z, translational and angular acceleration. So it calculates the inertial forces for all 6 degrees of freedom, calculates the mass of modeled beam and plate elements for inertial load generation automatically. So once you model it, it will calculate all the inertial loads from the modeled beams and plate elements. It has capability and generates member distributed loads and joint concentrated loads. So it's creating the member distributed load as well as joint concentrated loads and generates. Supports joint concentrated, member distributed user defined weights to account for non-model items. There may be some items it's non-model item, like some kind of equipment weight or something. So to account for those non-model items weights, it is supporting the joint concentrated and member distributed user defined weights. Allows user defined loads to be specified in load input files in the tau input file. An option to consider loading specified in the model file when creating inertial load. So when we are having the loads specified in the model file, so we can use those loads to create the inertial loads. So those options are available. Ability to orient and reorient structure within the tau input file for any particular inertial load case to be created. So we can orient and reorient for a particular inertia load case. So we can change the orientation in the tau input file, within the tau input file itself of the structure. Orientation of the structure we can change it. Ability to convert any load case in the SACS input file to weights. So whatever the load case we define in the SACS input file, it can be converted into weights. Allows factoring or any SACS load case when converting to weights. Okay, so we can put the factor also in the model file. If we define some equipment weight, say 10 tons, and if we want to factor it up with some factor, so like 1.2, some 20% more, that can be done in the tau input file. Optionally considers the weight of grout. So weight of grout also it considers. Ability to calculate the acceleration data based on user defined pitch, roll, yaw, angle and period. So if we define only the roll angle, yaw angle and pitch and period, it can calculate the acceleration data as well. In this video we will explain about determining inertia forces. In SACS program, the tau program module generates the reverse effect or d-element inertia forces in the opposite direction of applied translational or rotational accelerations. There are two accelerations. One is translational acceleration, translational or linear accelerations. Another one is rotational or angular accelerations. These translational linear accelerations in the figure below, if you see it, for any point on the structure with a mass m, the inertia force Fa due to a translational inertial acceleration vector is determined Fa equal to minus m times a. That's minus is the reverse direction, m is mass, a is the acceleration. The force component acting along an x-axis is nothing but Fax equal to minus max, where ax is the component of the acceleration vector along the x-axis, that is ax equal to a cos beta. Here you can see this acceleration Fa is right. So this component will be a times cos beta. This is the beta, so it will be cos beta. It would come. The tangential acceleration theta delta theta and centrifugal acceleration delta w. So there are two types of acceleration. One is the tangential acceleration, another one is centrifugal acceleration. So there are two forces. Here you can see this delta theta is the r times theta double dash, and delta w is equal to r times omega squared. R is the distance between the center of rotation to the center of gravity. So the difference between translational acceleration and rotational acceleration is this r. That's the distance between center of rotation to center of mass. We can say center of gravity. That's the difference. The tangential acceleration theta delta and the centrifugal acceleration theta omega due to the rotation of the structure may be taken as follows. Due to rotation of the structure only, these both centrifugal acceleration as well as tangential acceleration. This is the tangential. Centrifugal is towards this center of rotation it would act, where omega and or the angular velocity. So here omega is the angular velocity and acceleration about the center of motion. Here you can see this omega, right? The tangential and centrifugal forces are F theta equal to minus m or double dash, and omega is centrifugal force and tangential force. The component along axis x of the rotational inertia force F theta and F omega are theta x equal to minus m into r then theta double dash sine alpha. This alpha angle is there, and F omega is that minus m into omega squared r cos alpha. Here if this combining all these total inertia forces along the x-axis, minus m ax is the linear acceleration, r double r times theta double dash into sine alpha plus omega squared r cos alpha. This omega squared, if the angular velocity is negligible, then total inertia force will be reduced to only these two terms. This is the linear acceleration, this is the angular acceleration. This is due to translational force, not centrifugal force. The tau program assumes that mass m is positive mass and equal for all directions. This is very important. Tau program assumes that the mass m is positive mass and it is equal for all directions. Here last time we have seen the angular velocity is negligible, means the total inertial load along the axis is Fx minus m ax, that's linear acceleration, and r theta double dot sine alpha, that is the theta is the angular acceleration, that's a tangential acceleration. And the tau program assumes that the mass m is positive mass and equal for all directions, creating inertial load. If you see here modeled elements in program, we can model some elements. So for if the beam element is modeled, mass m in equation 4, this equation 4 is a mass per unit length, and for each segment of the element a member uniform inertial load is created along the length of the segment based on the mass per unit length and average acceleration of the segment. If the member is like this two joints, it will take the average acceleration at these two position, and then the mass of the segment it will calculate. Plate inertia load is calculated based on the plate plate total mass. So if you see here, this is the plate, and it will take the plate mass completely, and acceleration at the plate centroid. You can see the centroid of this, and acceleration at this point, and completes the total mass of the plate. It will calculate the inertial load, and then the inertial load is applied at the plate corner joints. These are the corner joints. So these corner joints, the inertial load will be applied for plates. User defined weights and loads. If you see it here, user defined weights, the uniform inertia member load is created for a user defined member distributed load or weight. We used to define some non-modeled weights, so it will calculate that weights as a uniform member load. The specified load or weight is converted into positive distributed mass regardless of the load direction and the sign specified. So when we specify mass or weight that will be distributed mass, that's a positive distributed mass regardless of the sign or load direction. In the inertia load is created from a user defined member constant at a load or weight. The specified load or weight is converted into positive mass regardless of the direction of the load or the sign of the weight. For a user defined joint weight, for a user specified load on a joint, the inertial load is created. The specified weight is converted into positive mass regardless of sign. For a joint specified loads, the mass is determined from the vector sum of x, y, z direction loads on the joint px, py, pz and respectively, and divided by this acceleration due to gravity. Suppose if one joint is there, we have applied the load fx, fz is 10 kilonewton and fy is 10 kilonewton and fz is 10 kilonewton, like that all three directions. If we apply 10 kilonewton, what it would do, it would convert that mass as a square root of 10 squared plus 10 squared plus 10 squared divided by g. G is the 9.81. So from kilonewton you need to convert to newton, then from newton you can divide by g, then you will get the kilogram. Then if you divide by 1000 you will get the tons. The tau program requires a SACS model file and tau input file. The model file requires no special modeling consideration for the purpose of inertial load case generation. So when we want to try to create the inertial loads, then there is no special modeling consideration. So whatever the model is there, it would generate the inertia forces by tau input file by giving some specified options. So general options, if you see the tau analysis options are specified on the tau option line. Enter the input units in columns 9 to C. You can see this a little later. EC in columns 11 to for the input data to be echoed. If you want the input data to be echoed, then we need to enter EC. EC means input data to be echoed. If concentric tubular sections are to be considered grouted, then we need to give a GR in columns. Suppose if you are considering the grouted members also to be transported, then we need to include this GR option. That will be included in this 25 to 26 to include the weight of grout. Usually we don't do this kind of options because whenever we are transporting it, it will be jagged at some cargoes. Some rare cases we may be having this kind of concentric tubular sections with grouted while transporting. Excluding the weight of the model. By default, the weight of the model elements is included in the inertial load generated. The weight of the model can be ignored, however, by inputting the LO in columns on the tau input line. So if you want to ignore the model items weight, while generating inertial loads, then we can use the option LO. The load cases generated would contain only the inertial load due to any load cases or user defined weights converted into inertial load. This option LO, if you put it, then it would convert only the load cases generated would contain only the inertial load due to any load cases or user defined weights. Structure orientation. Normally the structure would be rotated to the proper orientation and position on the barge in the model file such that the global structural axes are aligned with the barge axis. This allows the user to generate the inertial loads due to surge, sway and heave linear accelerations and road pitch angular accelerations along both the structural global axis. See the figures on below. Normally the structure will be rotated to the proper orientation and position on the barge in the model file such that the global structural axes are aligned with the barge axis. Actually there are two axes, one is the barge axis, another one is the structure axis. This allows the user to generate inertial loads due to surge, sway, heave, linear accelerations, roll, pitch, angular acceleration along or and or about the structural global axis. So we need to generate the linear acceleration forces as well as angular acceleration forces. The inertial loads may be generated in any direction and are not required to be generated along the structural global axis. However, orienting the structure in the model so that the global axes are aligned with the barge axis, that will allow the user to verify and visualize the transportation results quite easily. So by doing this we can visualize the results quite easily. By default, the position of the structure model is used in the tow analysis. The structure may be repositioned for any inertia loading cases created using position line. When orientation angles are specified, the structure is rotated about the global x-axis first, then global y-axis followed by rotation z-axis. It means like that we can reposition the structure in the bar so that we can generate the inertial loads. When the structure is repositioned using the position line, the new position is retained for all subsequent inertial load cases until the new position is defined. So we will learn about the center of motion. Center of motion is the point about which the barge structure as a system rotates when subject to transportation forces. So when the transportation forces are when the structure is subject to transportation forces, then about this point only entire system is rotating. So that point is called center of motion. So these forces induce pitch, roll, and these are the motions, angular motions. XYZ coordinates of this point are specified in the tau input file. You can see in the tau input file there is option called tau option and are defined with respect to the model global coordinate system. With respect to the model global coordinate system, we can see the model global coordinate system. From that system, how much distance in x and y and z axis, z coordinates. Enter the global xyz coordinates of the center of motion in column 31, 38 to 44, 51, 45 to 51. The following designates the center of motion is defined by the global xyz coordinates. These are the coordinate with respect to the global coordinate. Center of motion is x. In x direction 8 meter away and y direction is 23.5 meter away, z direction 13.67 away with respect to the global coordinates. Here you can see with respect to the model global coordinate system. The origin of tau or transportation local coordinate system coincides with the center of motion specified in the tau option input line. So origin of tau or transportation local coordinate system and center of motion. Here you can see the rotation center. So this is the center of motion that will be specified in the tau input line. The orientation of the tau coordinate system is defined by the user by specifying the model global axis that corresponding to surge, roll or sway, pitch or heave and yaw. Enter the structure global axis corresponding to the surge axis in column 52. If you see here, this is the we have to define what is the surge axis. This is the surge axis, that's with respect to the x, and with respect to y, like that we need to give the structural global axis. Which global axis is corresponding to surge axis? For example, here the global y axis is corresponding to the surge or roll, and global x axis corresponds to the sway or pitch, and z global axis corresponds to the heave and yaw. That's how it's defined in this example. Here you can see yx is at y, that corresponds to surge and roll. So whatever we define it in the column x2, that's uh, structural global axis, that's the surge axis. So here you can see this is already surge axis, sway and heave. So we need to align our model by by specifying the global axis of the model. So in the following figure, global y-axis, here global y-axis is the surge axis, global x-axis is the sway axis, and global z-axis is the heave axis. So this is the example. LCFAC line is there here. This factor 1.0 is used to convert EQP1 EQP2 load cases 100% for these two motion parameters, roll plus E1. 12.0 roll degree, 10 is maybe the seconds, and 0.2 is the heave. And LCFAC, this line with 0.5 factor is applied for these two load cases, EQP3, EQP4. Note, load cases selected to convert to weight, replace any previous load cases selected and used for all subsequent initial load cases created either by motion or acceleration until another load cases are selected. In the above example, only load cases EQP3, EQP were used for load case R plus H2. So R plus H2, it will use only the load case EQP, EQP4 only. Converting the first load case. If the model file contains only one load case, it may be converted to weight by specifying LD columns in the 13-14 line of the input file. LD option is provided for backward compatibility purposes only, and should not be used in the conjunction with the LCFAC line. So LCFAC line, if you are using it, we should not use this LD option. Converting model loading to weight. Inertial loads for non-model items defined by member concentrated, member distributed and joint concentrated loads specified in the model file can be converted to weights automatically by the program. That means inertial load, whatever non-model members we are defining, like a member load or member concentrated load, member distributed or joint load, that can be automatically converted into weight by the program. So what it will do, we usually apply the loads in for example, member is that we apply load as 10 kilonewton. Then what it will do, it will automatically convert this 10 kilonewton to corresponding mass, like 10 kilonewton divided by 9.8. If you put it will come as roughly 1 metric ton, right? So that will apply. So by default, when the member distributed loads are converted to weight, they are treated as a member distributed weights. Member distributed loads may be converted into joint weights by specifying ND. So if we specify the ND option in column so in the tau input file, it will automatically convert the member distributed loads into joint load. But usually if we are distributing as a distributed load in member, in inertial load also we prefer to have the distribution over the member inertial loads also to be designating load cases to be converted. Load cases in the model file that are to be converted to weight are designated using LCFAC line. So LCFAC line should precede any acceleration or motion lines defining inertia load case that are to include these weights. So we need to define this LAC line before we apply any acceleration, so that this LAC line will convert whatever the loads applied into weights. That weights will be subjected to these accelerations and the motion lines. Then it will calculate the inertial loads. The load cases may be factored when converting to weight by specifying appropriate factor on the LCFAC line. So we can even give the load factor. Suppose if this 10 kilonewton we have defined as a equipment load on condition, that equipment load condition we can call it in LCFAC line, and with the factor, if you want to put some 20% more, we can use that one. That's what this line is useful. In the following example, 100% load case of EQP1, EQP2 are to be converted to weight when generating the initial load case roll plus E1 and defined by the first two line of motions, and 50% of load cases for these two are to be used while generating the load case R plus H2 defined by third motion line. This we can see in this one example. Additional weights may also be specified in the tau input file using the joint weight and member weight input lines. In order to include user defined weight, the weight input lines should be specified prior to the motion or acceleration input line used to define the inertial load cases to be created. So what they're saying that if you want to input some weight input lines directly, we can define it for a joint weight or member weight, but it should be defined before the motion or acceleration lines, because these motion and acceleration line input will give the accelerations only. So to create the inertial load cases, we need to define the weight. Here you can see this weight 599, that's the joint, 20 is the load. So here a load of 20 joint 599 defined by weight input line will be included in the first inertial load case along with the constant load of 20 on member. You see this member, this is a member, this is a joint, so this member weight also 20. So this will be used to create the acceleration for this acceleration 1.0, like that it is there, right? The specified weights will be included in all subsequent load cases created unless overridden by new weight inputs. So here new weight input, if you see it, weight input 599 0.0, that means next this acceleration load it will create 0 only because 0 mass. When specifying weight data, all weight data defined for previous inertial load case are replaced. Therefore all weight data may be removed for inertial load case by specifying 0.0 weight. Member constant load, member distributed joint constant load input lines can be entered directly into the tau input file after position input line. Tau ops line, if no position line input line is specified, no modifications to the load input lines are required, the program will automatically create the corresponding weights. The tau program can use weight groups defined in C-state input file to specify inertial loading. These weight groups are specified on the include weight line. So tau program can use weight groups defined in the C-state input file. Sometimes in C-state input file we can specify the weight groups to specify the inertial loading. We can define it. These weight groups are also specified on the include line. For example, the following line indicates that weight groups 235 will be used to create inertial load cases. These weight groups must be defined in the C-state input file. So once we define it in the C-state input file, these weight groups, it can be referred here in the tau input line using include weight groups 235 like that. So generating inertial load cases containing inertial loads due to translational linear acceleration or rotational angular acceleration about the global axis are created based on either motions or accelerations and defined using either motion or acceleration input lines respectively. Either we can use motion input line or acceleration input line, so that we can create the inertial load cases based on either motions or accelerations. Inertial loading is generated automatically for any beam or plate in the model based on its modeled weight. So inertial loading, it will be created automatically. So once we define it in the model, it knows the weight. So based on that modeled weight, it can create the inertial loads. In addition, inertial load is developed for any loading converted to weight and user defined weights. So if we define some unmodeled items also, we can convert them to weight, and then inertial load can be generated for those converted weights, user defined weights. Inertial load is created in opposite direction of the imposed acceleration. So acceleration is minus x, means the forces, inertial force will be created in the plus x using d-element forces and are calculated based on the structure's current position. There is a latest position line encountered, the current selector load case and factors. The latest LDC data specified and any load factor under for weight input lines defined prior to motion acceleration line defining the accelerations. Specifying motion data. The tau program can create inertial load cases based on the accelerations defined in the motion data input or by the user or the motion line. A unique load case is created for each motion line. Specify the load case name in columns A roll angle period defined in columns, and the pitch angle and period in these columns, yaw angle and period in these columns. So when the barge is rotated by a roll or pitch angle Q, the weight of the structure applied vertically down contains a component of normal to the barge calculated as cos Q, and the component parallel to the barge surface called a sin Q. The tau program can automatically include these effects of gravity on the translational inertia forces with the include gravity option in column 77. If heave is assumed normal to the barge, enter G in column 77 to include the gravity component of surge, all these things. Enter L to include gravity component only surge and sway, lateral forces only. If heave is assumed vertical, enter H in the column 77, gravity component of surge. Enter V to include only the surge and sway, lateral forces only. Leave column 77 blank to exclude the effects of gravity, or if the translational acceleration input already includes the appropriate gravity component. The center of motion used for this inertia load case may be overridden in columns 56-76. Inertia due to the structural weight may be ignored by specifying n. This is especially useful if the motion load case will be combined with the dead loads. This way the structural weight will not be included twice. Following defines inertia load case: r plus h1, r minus h1, roll angle 15 degrees and period 10 seconds. The first load case have a heave acceleration of 0.2, second has a heave acceleration of minus 0.2. Both have the program to include the effects of gravity automatically. Here it's defined G. These are the roll angle, roll period, and heave. Specifying acceleration data. The acceleration ACCR line may be used to specify accelerations used to generate inertia load case. A unique inertia load case is created for each acceleration line specified. Here you see the acceleration line is specified. For each acceleration line there will be a unique inertia load case. It will be generated. Enter the name of the load case in column 7 to 10 unless the name of the load case is to be determined by the program based on the next available numeric load case. That means if you don't specify, it will be generating the next available numeric load case name. Applicable XYZ axis angular accelerations are specified in degree per second squared, and translational or linear accelerations are expressed in G's in columns respectively. For example, the following creates a load case containing inertia load case due to a linear acceleration of along the global x-axis of 1g. So linear accelerations are expressed in terms of g's, and angular axes are specified in degree per second squared. The effect of gravity is not automatically included when generating inertia loads using the acceleration line. Gravity load may be created by specifying 1.0 g acceleration in the z direction. Specifying allowable stress modifier inertia load cases. Allowable stress modifier may be specified for any inertia load case created using the A-mode line. Using the A-mode line, we can create the A-mode lines. A-mode line, we can create the allowable stress modifier. Specify the load case name or appropriate and the appropriate factor. For example, the following creates inertia load cases R plus H1 and R minus H1. Allowable stress modifier factor of 1.33 is applicable for both load cases R plus H1, R minus H1, 1.33, 1.33. A-mode line must contain the header line and must follow directly after the tau input line. A-mode must follow directly after the tau input line. Alternative motion data. Motion line provides alternative to the motion line in creating inertia load cases. The motion line is based on the inertia capabilities of the C-state program. As such, a C-state input file is needed to make use of its full capabilities. So what they are saying that the C-state input file is needed to generate this alternative motion data to make use of its full capabilities. The MOTN motion line load case name is specified. Here you can see the load case name R plus H1 is specified. The roll, pitch, yaw angles are
and periods are specified. Here you see the 15 is the roll angle and 10 is the seconds. First load case have a heave acceleration of 0.2. Here you can see 0.2, while the second has a heave acceleration of minus 0.2. Both have the program to include the effects of gravity automatically. By specifying G, we can include the gravity automatically. Neither excludes the structural weight. The center ID for these load cases, center ID CEN2, was specified here. The translational acceleration components are specified in column 1, so the effects of gravity include automatically with the G in column 74. The structural weight is excluded from the load case with N if we specify. All these options are similar to motion line. The MTO line, MOTN line has added feature of specifying center of motion for rotational accelerations and velocities. This center is identified in columns. So this is the, you can see this CN2, this is the center of motion feature for specifying, added feature for specifying center of motion for rotational accelerations and velocities. This center must be defined in the C state input file. The following defines the inertia load cases about what discussed. Okay, alternative acceleration data. ACCL line provides an alternative to the ACCL line in specifying accelerations to create inertia load cases. ACCL line is based on the inertia capabilities of C-state program. It is based on the inertia capabilities of C-state program. As such, a C-state input file is needed to make use of its full capability. So we need to create a C-state input file. ACCL line, the load case name is specified. Translation acceleration components, we can specify. The rotational accelerations also specified. The effects of gravity are automatically included with the G. The ACCL line offers two added features when compared to ACCL line. One is the specification of angular velocity for computation of centripetal accelerations and specification of center of motion for rotational acceleration and velocities. The center, this center identifier is specified in column. This center must be defined in C state input file.
Output reports including the member data, plate data, added weight, and load summation are designated on the tau input line, tau option line, or designated. Enter MP in column 17 to 18 to print the member data report, PP in columns to print plate data report. MP means member report, member print, plate print kind of thing. WP means might be for the user defined added weights. Inertial load summation reports may be generated about the model origin, center of motion, or center of gravity. By specifying origin, or C is the center of motion, and gravity, rotational center, and gravitational center, center of gravity. Joint spatial reports. This is very special reports. The location and acceleration for up to 16 joints can be reported for each inertia load case created. The location and acceleration reported in both model, global, and tau local coordinate system. The joint names are specified in the tau input files on the JT joint number input file. Input line. In generating rigid body mass matrix, the program can generate a rigid body mass matrix including mass of all members and plates included in the model. Any load cases converted to weights in addition to any weights or loads defined in the user input file also included. The following designates the rigid body mass matrix generated for the model including mass due to load cases EQP1, EQP2, defined in the LCFAC line, EQP1, EQP2. Calculating motion response due to RAO input, that is response amplitude operator. This tau program can calculate the inertia response loading for various points along a wave cycle based on a response amplitude operator input by the user.
response amplitude operator data input. So we need to give this data input, data's input response REO data, and typically for a particular wave direction, acceleration, velocity or displacement response operators are designated for various wave periods using REO lines. Here for example, this wave period 25, this wave period 20 seconds. For example, the following input source REO data for wave periods 25 and 20 seconds. Okay, from this data the inertia loading can be generated for various phase angles of desired waves designated in the wave definition line. So some waves will be defined in the wave definition line. For those desired waves of different phase angles, various phase angles, we can generate the inertia loading. A set of RAO and wave definition lines is designated for each wave direction when considering the multiple wave directions using different response operators. Okay, a set of RAO and wave definition lines. The loading due to a designated wave is assumed to be from single amplitude response, where the wave height is assumed to be double amplitude. For example, unit displacement RAO would yield a displacement equal to one half of the wave height. Okay, RAO input response amplitude data is input using a series of RAO lines for a particular wave direction question. RAO line is used to define the response for a particular frequency or period. This is a particular frequency or particular period. Enter the amplitude type in column A as A for acceleration, or V for velocity, D for displacement, or G for acceleration. So here we are giving G. G is the acceleration. So these are accelerations. Enter P for the period or F for the frequency. Here P is the period. So P or F. Designate the surge sway, heave, roll, pitch, amplitude and phase angles corresponding to this period. So you have to define all these surge, sway, heave, roll, pitch and corresponding phase angles to this frequency. One REO line is required for each frequency or period. Here this period 20 or 25, one REO line is required to define the response. Wave definition lines are used to designate the waves for which the responses are to be determined. So whatever the waves we are trying to get the response, that we need to designate in the wave definition lines. For each wave height, period must be specified. So wave height and period must be specified in the columns 15 to 20, 21 to 26. So here you can see this is the period and wave height might be. Here you can see this is wave period of 20 and wave height of 30. The following specifies the response for the 18 points of wave. So this is 18 is the nothing but 18 points of wave with height of 30 and period 22 are to be generated. The wave direction is 45 degree. Here you can see 45 degree. The first load case to be named A01 and the second 45 degree with the wave of period of 20. So wave period 20 is also mentioned, 22, 20. The first load is to be named B01. Load cases due to response from a set of 90 degree waves are also indicated by a second set of RAOs. Here you can see this is second set of RAO and wave definition lines. This is for the 90 degree. So here what we can understand that the number of points per wave cycle to create loading is specified, while the load case of the load case name of the first load case to be created in input lines also given. Enter the wave direction. If structural weight is to be excluded from the load case generated, then specify n in column 75. That's not specified here. This is useful if the load case generator is combined with jet load cases. This way the structural weight will not be included twice. Or more in the load case. RAO data is interpreted for periods not defined by an RAO line. If that period is not defined, then RAO data will be interpreted. However, RAO data should not be extrapolated for waves with periods higher than
the highest ROA period are lower than the lowest ROA period. Okay, so this ROA data, it will not be extrapolated for waves with periods. Here wave period is 20 is given, right? So for this, it will interpolation it can do, but extrapolation it will not do it. So note, REO line must be added with a period higher than the wave period if the wave period is greater, and then highest RO and then the highest RO period. Likewise, REO line must be added with a period lower than the wave period if wave period is less than the lowest REO period. That's clear. Note, interpolation will be used for the first wave in each direction since no REO period corresponds to 22 seconds. Here 25 and 20 is there, so it can interpolate between these two. This is the period for the REO. Automatic load case generation from REO input. Load case data is automatically generated based on REO input by using LC REO line. Load case REO line. The load case REO line is used to define REO characteristics to be used with response amplitude operators to calculate the responses. It is normally used in tau fatigue analysis to generate the transfer function of hotspot stress. So LCREO, this line is used for mainly for the tau fatigue analysis to generate the hotspot stresses. For each period or frequency in REO lines, LCREO line will generate load case starting from the load cases specified in column 7 to 10 of the load line LCREO line. For example, here it's 45 degree R plus I. That's the load case analysis. So if columns 7 to 10 are left blank, the load cases are generated automatically, numbered consecutively in order for case now starting from 1. The wave direction in degrees is specified in column 11 to 16 of the line. So here it is 45 might be the wave direction. Here we will see the load case REO line gives two options for load generation, R plus I and NPT. The R plus I option will generate two load cases, real and imaginary, for each period and frequency of REOs. Two load cases are to be used in fatigue analysis with the R plus I option specified in FTLOAD, fatigue load data records. NPT option will generate the number of load cases specified in columns 20 to 22 to complete cycle for each period frequency in REOs. The following input source REO data for wave periods 25 to 20 seconds. This 25 to 20 seconds. Two load cases, real and imaginary, will be generated per REO with wave direction of 45 degrees. These loads are to be used in fatigue analysis with the RI option specified in FT load data records. Alternative REO input. Another method of entering REO data is applied with INC REO line. This line allows user to input REO data from the C state input file into the program. Unlike other inputs methods for REOs, the INC REO offers the capability specifying the velocity dependent REOs. The velocity of the REO is specified. If English units are used, input velocities must be used in knots per feet. Is specified as per second, FPS, feet per second. The following example will be generate inertia loading for a wave speed of 2.5 feet per second. This line is only used for REOs defined in C state input file. If velocity values specified in INC REO line do not correspond to the velocity values in C state, interpolation or extrapolation will be used to obtain values.